Hey guys, today we're going to talk about physics and engineering applications from section 8.3. The first one we're going to talk about is hydrostatic force. A hydrostatic force is the amount of force that's exerted on an object that's underwater, or maybe an object that's like at the end of a water tank. So before we go any further, let's talk about the difference in force and pressure. Force is the amount of push or pull on an object, and it's measured in pounds or newtons. Pressure, though, that's force divided out by area. So an example of that would be tire pressure. It's measured in pounds per square inch. So if you go down deep underwater, the pressure gets high because it's because of the weight of the water above you. And an example of that, let's say I had this disc here, which is the top of a lid to something, and this disc, which is a battery. If I were to take both of these and put them at the bottom of a pool, they'd both be experiencing the same pressure, but this one would have more force on it because it would have that pressure exerted over every square inch of it here, or every bit of area. This would have the same amount of pressure, but over a smaller area. So equal pressure, but more force on this than on this. Now, the computations that we're going to do here, they're similar to the ones we did back when we were doing the water pumping stuff. So we're gonna split this up into a couple of parts. First, we're going to look at hydrostatic force on things that are horizontal, and then we're going to look at things that are vertical. So the horizontal ones are going to be the easier ones. So let's go ahead and look at that. It says these problems are calculus-free because the pressure over the entire plate is the same. So yeah, if you've got this down at a certain depth, really all you have to do to compute the force on it is just figure out what the weight of the column of water is above it. So let's start with this one. Consider a round metal plate on the bottom of a swimming pool. Suppose it's 12 inches across and 10 feet underwater. How much force is on it? All right, so you've got a round plate here, and you've got a 10-foot column of water above it. So really all you have to do is compute the weight of this column of water. So this is really just a geometry problem. Let's see, if it's 12 inches across, let's see, the area is going to be pi, the area of the base is going to be pi times the radius squared. Now it's 12 inches across, so that means that its radius is half of a foot. So we get pi times 1/2 squared. So that's pi times a fourth, or pi over 4. Now the depth, the volume of water then, is going to be pi over 4 times, let's see, how deep was it? 10 feet. So that's 10 pi over 4, or 5 pi over 2. And that's in cubic feet. And so the force that we're dealing with here is going to be 5 pi over 2 cubic feet times the density of water. So this is done in feet, so it's going to be 62.5. And again, that comes from water weighs 62.5 pounds per cubic foot. So I just need to multiply this out. 62.5 times 5 over 2. This gives me 625 pi over 4. Let's actually get that as a number. Well, that is a number, but let's get it as a decimal approximation. 490, I'm going to round to the nearest whole number. 491 pounds of force. All right, so 491 pounds of force on that plate. Okay, let's do another one. Another pool is 5 meters deep and has a rectangular plate on the bottom that's 20 by 30 centimeters. Find how much is the force on this plate. Okay, so we've got a plate down here. It's 20 centimeters and 30 centimeters. So I'm going to convert those into meters. And then the column of water on top of it. The volume of water is 0.2 times 0.3 times 5. So let's see, 6 times 5 is, what is that? Well, 0.2 times 0.3 times 5 is, yeah, 3/10. 0.3 cubic meters of water above it. And now we have to convert that to from cubic meters into newtons. So you multiply by 9,800. So force is 9,800 times 0.3 is 2,940 newtons. And of course, that 9,800 is the density of water. It's the weight density of water. I spelled that wrong, but that's okay. In newtons per cubic meter. And of course, if you want to, you can break it up into force equals mass times acceleration. F equals ma. This right here is the, if you were to break that up, it's 9.8 times 1,000 times 0.3. This right here gives you the mass. This right here is the acceleration due to gravity. So you can't take this back and write it like, Newton's law, F equals ma. But as far as I'm concerned, just memorize that 9,800 is the weight density of water in newtons per cubic meter, and 62.5 is the weight density of water in pounds per cubic foot. Okay, now these problems were relatively easy because the plates that we looked at on both of them are at the same depth. Every part of the plate is at the same depth. They're both on the bottom of these pools. It's going to get more complicated in the ones that we do in the next video, where we have vertical plates or the end of a tank. So we'll start that in the next video.